Okay, so today we will look into another techniques, okay, that are being used for so-called design, okay, and what you have learned yesterday, okay, and 2 weeks back, okay, is one of the technique we call it root locus technique, okay, where we try to observe the locations of the root locus, and by doing that, we are able to like identify based on the locations what are the characteristics that we would desire to, okay, and from there we estimate, okay, what are the proper gain to be used. Okay, so today we have another technique, we call that as a frequency response technique, and the goal of the day would be the ability to draw a board diagram, okay, board diagram, and evaluate the frequency response for a given system. Okay, so just a little bit of recap. Okay, you have seen this slide before, and we have mentioned that we when we are dealing with a closed loop transfer functions, okay, therefore our transfer functions will become slightly difficult, okay, slightly more difficult in terms of the denominator, which is 1 plus kgh, okay, which we cannot factor it out as easy as it is, okay. Therefore, we need this kind of technique like root locus technique, okay, as well as now we would like to use another technique, we call it a frequency response technique, okay, uh, where we would like to see, okay, for the closed loop pools, okay, how it would change, okay, when the system gain, the k value change, okay. So here is the comparisons between the root locus and the frequency response, okay, based on the books lah, right? So here they say that root locus may give a lot of information in terms of because we understand the S plane, okay, and from there root locus will provide us with a more understandable visual aid, okay. But however, when we want to analyze the performance of a system, okay, for example, much higher than the order of the system much higher than 2, and also when we start to uh, deal with problem that are not directly obtained from theoretical, but yeah. So in those cases, okay, we would like to have another way of analyzing it, okay, in from the point or from in terms of frequency, okay. So the root locus many times we somehow is related to the time response, okay, how we will see the time response curve where you have uh, the oscillations, okay, maybe a sinusoidal performance, okay, according to time, okay. So much more easier for us to visualize because we can easily visualize the time as the time zero, okay, what is the location and so on, okay. But then sometimes the system doesn't stop, okay, it keeps repeating itself, okay. Therefore this frequency response will be a much more ideal methods, okay, to evaluate how a system will respond to probably a kind of repeating, okay, like sinusoidal inputs, okay, which are commonly used maybe in experimental as well, okay, as well as some real cases, okay. So here the expected output, okay, would be a waveform, okay, because of the input itself also is in the form of wave, right? So as we can see a typical spring mass system, okay, if we just push the mass, okay, with a force, okay, therefore when we release it, okay, no more input to the system in terms of force, therefore the system will just oscillate lah, right? Quite straightforward. But then if we intend to provide the input of the force in terms of frequency, okay, or in terms of repeating input, okay, sinusoidal types of input, therefore the response will now behave differently, but as we would expect, is in the waveform format as well. Okay, so here is the frequency response, okay, where it will shows how a system respond to a sinusoidal input. Okay, so typically when we deal with frequency or sinusoidal input, therefore we always deal with the so-called polar form, right? Polar form. Okay, so if we have this spring mass system, okay, and we try to plot them out, okay, plot them out, if we are giving this kind of input, okay, where this input is not starting from zero, okay, it start from somewhere shifted by phi I, let's say, okay, therefore we would write the magnitude, okay, maximum magnitude m, okay, with a phasor, okay, phi input, okay, phi I lah, right? So we will write it in this form, okay. Therefore, these systems will now give a kind of reaction or actions to our spring mass system, and our spring mass system will produce the kind of output, okay, and the output would be given as probably in MO, okay, output, okay. Again, this is the phasor output, okay, phasor output, okay, phi O, okay, which would be equals to the original, which is the input, plus there is a difference in terms of the phi, right? So we put it as this way lah, right? So how we can visualize this so-called sinusoidal itself, okay, in terms of this phi phasor magnitudes, okay, or phasor length. This length actually being described by the m, okay, and this angle, okay, this phasor angle basically is the rotations, okay, the phasor angle, right? So this is the basic mathematics behind this phasor length, phasor magnitudes, and so on, right? So now, in order for us to find the frequency response, okay, we would first observe the input, okay, the RT itself, which could be described by a sinusoidal equations. Okay, we have maybe A cos omega t plus B sine omega t, right? And if we take this into the Laplace transform form, so it would be AS plus B omega over S square plus omega square, right? Though we assume that maybe the initial condition would be a zero, okay? Therefore, the output would give us in this form as well. Same output, right? Same output lah, AS plus P omega over S square plus omega square, okay? But the output would require us to multiply by the transfer functions, right? That GS, right? So for us to now separate this one, okay, we would separate it, okay, the force and the transient solution. So we separate it by taking the partial fractions, okay. So taking partial fractions, then we realize that the K1, okay, K1 would be the M1 mg, right, divided by 2E minus J with the phasor angle, right? Whereas the K2 would be again mi mg over 2, same thing, right? So same yeah, probably same, because they are in the form of conjugate, right? In the form of conjugate in between them, right? Whereas the mg would be the magnitude of the g omega, okay, gj omega, okay, and the phasor will be the angle of the phasor angle lah, g omega, okay, of that particular phase diagram, okay, phasor diagram, right? So in terms of steady state response, then we would have, okay, basically this one, okay, when we write in terms of in this form, therefore we would give us mi mg cos omega t plus the angle of input plus the angle of the due to the gain itself, okay. So in other words, we can also write in terms of m output, okay, with the angle of phasor output, all right? So this is how we may get lah, okay, in the form of mathematics, okay. the details of this response can be derived in such. Okay, so this one I may not go in detail, right? So you may just take your own time, okay, just see how all these things are being substituted, okay, and get it out lah, right? So basically all this would require to refer to some of the Laplace transform and the phases diagram conversions or table, right? Okay. So how we can visualize this frequency response would be in terms of a polar plot, right? A polar plot. So the function of the frequency, we will separate it as the magnitude as the phasor plot, okay? Or we call that as a polar plot, which consists of the phasor length and also phasor angle. Okay, so these two things, okay? Phasor length, probably the magnitude, and the phasor angle. Okay, and this is what we intend to do today. Okay, plotting the magnitude and the phase plot, okay, for the system, or maybe a closed loop system that being subjected to a sinusoidal input, right? So here we will notice that the magnitude curve can be plotted in terms of decibel, okay, dB, okay, versus log omega, okay. Since the so-called omega, if we put it in terms of the linear form, okay, therefore it may require a very long table, okay, or maybe long plot itself, okay. And we also would see that there is a relation between these two in terms of exponential, right? The equations consist of the exponential term, okay. Therefore, we can use the log, okay, so that we will form a linear line later on, right? So the definitions of dB here, okay, 1 dB, we would define it as 20 log m, okay, 20 log m, right, in terms of dB. And then also the phasor curve, we will plot as the phasor angle versus the log omega, right? So we will use the x-axis, this log omega as our x-axis, okay? Whereas the y-axis will consist decibel to represent the magnitude, whereas the phase angle to represent the phase curve, okay? So this would be the logarithmic scale graph paper, right? So where you can see that this is in terms of log, okay, semi-log I would say this semi-log graph paper, because this one is log, this one is not log, so semi-log, okay. So we would put this as the magnitude, okay, and define it as maybe gain or magnitude lah. The unit would be dB. For the phasor one, we will use the phase, okay, the unit would be in terms of degree, okay? But the unit for the x-axis still the same, okay? Frequency, okay, probably in terms of radian per second, right? So this semi-log graph will be provided together with the question paper, right? So you don't have to prepare this one, you just have to use this graph paper and plot it on this lah, okay, in order for you to see the later on you will see how we will use this frequency response plot, right, the so-called magnitude curve and the phase curve, okay, for our main purpose, okay, of designing, right? So that would form what we call as that will form what we call as a dot plot, right? So our objective of today, ability to draw a dot plot, right? So that dot plot basically consists of these two things, okay? A magnitude and the phasor response, okay? So as we would see again, okay, any transfer functions can be like given by, for example, 1 over s plus 2, s plus 4. When we separate them, we will get this form, okay? Then we can basically represent this form, okay, in the magnitude and phase response format. Okay, so we can put it in this way lah. Okay, instead of maybe S, okay, then we would put it in the frequency form. Okay, J omega, right? So now the things will keep repeating. Okay, in the frequency J omega format, right? So meaning to say, these equations now, instead of S, we will put all J omega inside. Okay, so J omega square plus 6J omega plus 8. Okay, so when we combine these two together, okay, separate them properly, then we will have 8 minus omega square plus j 6 omega, right? So again, there is a real part, there is the imaginary part. Okay, when we insert our input in the form of frequency, okay, omega, our input will be omega, right? It's a frequency format. Okay, therefore the magnitude for this magnitude, there is two component of it. The magnitude would be the square root of the two components lah. Okay, square root of the square of the two component. Okay, x 8 minus omega square plus 6 omega square. Okay, and therefore we can now notice that, okay, when omega is less than square root of 8, okay, when it is less than square root of 8, okay, the angle would be in this form. Okay, when it is more than 8, okay, so you will see that there is a positive and negative form. Okay, therefore the angle would be in this form, right? So if we plot it out, it will be in tangent form. Okay, so this is how it may looks like. Okay, so how it would relates to our board plot now. Okay, those are the basic mathematical form, right? And we try to employ all this mathematical knowledge and form into commonly used tools, okay, in control, okay, so that we can communicate easily, and from there also we can extract some important characteristic from it. Okay, so the log magnitude and the phasor frequency response curve can be given as a functions of log omega, as I've mentioned previously. In the graph, the x-axis is in the log omega form. Okay, and from there we can approximate those relationship as a straight line. Okay, as I've mentioned, they when we use log, meaning to say they are somehow related with exponential. So that's why we can draw a straight line over there. Okay, let's take this simple general transfer functions. Okay, let's say we have k with a lot of zeros and a lot of pools. Okay, therefore the magnitude for this would be the k with the magnitude of all these things. Okay, so, straightforward. Okay, so now by working with the logarithms of the magnitude, okay, the upper side, okay, if we notice, okay, in log itself, the upper side, the zero part, okay, would become additions, because when we take log multiply, okay, log meaning a times b times c, when we take log, then it would be log a plus log b and log c, right? So the upper part, we would add them up. Okay, whereas the denominator side, okay, we will subtract. Okay, so it would give us a simplified way to operate, okay, this magnitude, okay, when we convert them into a logarithmic logarithms of the magnitude. Okay, so that would be a kind of advantageous over here lah. Okay, quite straightforward, just plus and minus. Okay, even though the equations consist of a complex fractions, right? Therefore, the total magnitude response can be, for example, for this form, okay, can be now become 20 log. Okay, this is one of the terms that we multiply, so log k plus this term. Okay, so this would be log 20 log this magnitude. Okay, plus. Okay, then divide, meaning to say we have to minus, so minus 20 log sm, okay, minus 20 log and so on and so forth. Okay, so we would use 20 log with the magnitude. Okay, because later on when we plot the dot plot, okay, we will use the magnitude in terms of dB. Okay, so all these 20 log m will now become 1 dB, 2 dB. Okay, so eventually we get number, right? For the phase frequency response, okay, therefore we would say that the sum is the sum of the phase frequency response curve of the 0 minus the sum of the phase frequency response curve of the pool terms. Okay, just plus and minus of all the magnitudes. Okay, so using dot plot, this simplified by using plus and minus, the algebraic of the sum. Okay, and also have to keep in mind we will use straight line approximation to all these individual response. Okay, we will see how it is being used now, right? So let's take this dot plot for G equals to okay. Okay, this transfer function, okay, G equals to S plus A. Okay, so take the simplest one. We forget about all the complex fractions. Okay, remember we have very complex, it can be a very complex fractions for our transfer function. Okay, so now we just use this concept. Okay, all these things can be add and minus. Okay, therefore we draw one by one all these term one by one. Okay, so we start with the simplest one. Okay, G equals to S plus A. Okay, meaning to say divide by 1 lah. The denominator is 1. Okay, therefore if we use this one, okay, we have to let S equals to J omega as usual because we are dealing with frequency response. Put it in. Okay, therefore this S now become J omega plus A, right? So if we extract them out, right? So therefore we have A times J omega over A plus 1, okay? Something like this, right? This would be when we take the S approximate J omega, okay? Now we would start to categorize them, okay, into low frequency and high frequency, okay? So at low frequency, we would say that this low frequency is where the omega, this omega value is near to 0, okay, meaning to say it doesn't oscillate, okay, near to 0, right? So if this omega near to 0, then this term become 0, okay? Therefore, this G J omega is approximate to A itself, okay, the A itself only, right? So therefore, when we put into our magnitude response, okay, in terms of dB, then it would become 20 log A, right? 20 log A, right? And it's a constant, okay? Now, for the high frequency where the omega is much higher than the A, okay, much higher than this A value, okay? Now, what happens is that when it is much higher than A itself, therefore, these terms will become a dominant, okay? The one become like somehow negligible lah. So therefore we would say it's near to A J omega over A, right? This one we assume we already add in, still not significant, right? So in this form, okay, therefore we can write A omega over A, right? Because this J in terms of phase is 90 degree. Okay, so we put 90 degree in terms of angle, right? So we now separate the J out, okay? Instead of using the operations of imaginary J, okay, we convert this J into the phasor angle, right? So this J now become angle 90 degree, right? Therefore, when we write this out, okay, we would have omega with a phasor angle 90 degree, right? So what you have to remember now is that in terms of magnitude, let's take this first, okay? In terms of magnitude, we have 20 log A plus 20 log omega A, right? Because we have A omega A, right? So 20. So when we combine them together, okay, add and minus, okay, therefore we get 20 log omega, okay, with a phasor angle 90 degree, right? So this omega also have a range lah, okay, because we would say that it's much more higher than A, so minimum must be equals to A, and it can go up to infinity, right? So what we would do now, okay, by this understanding, okay, for this simple transfer function S plus A, therefore we can say that the high frequency approximation, okay, this part, okay, this high frequency approximation is equals to the low frequency approximations when the omega is equals to A. This point and this point must coincide, right? So when the frequency is equals to A, this 20 log omega should be equals to somewhere near 20 log A, right? And from there, it will start to increase, okay, with certain rate lah, okay? So if we plot the dB now, okay, against the log omega, we would simplify in terms of a straight line, okay? We will use y equals to 20x, okay, with a slope of 20 because of this 20, okay? Therefore, when we use, okay, when we plot it, the magnitude in the plot now, okay, first thing is we need to draw the axis, okay? So this axis, this 10 with the power of 0 means 1, okay? And that probably represent the A value, okay? The A value that we start, okay? Then every time it becomes 10, 100, and so on. Whereas here we divide by 10, divide by 10. So therefore we have 0.01, A, 0.1, A, and so on, okay? That is the magnitude plot, okay? So plot it accordingly. And on the y-axis, we would put like 0, then 20 log A, then 6 plus 20 log A, 12, so on, so on, so on, so on. So you will see that every time it increase would be in the form of 6, 12, okay? We call that as 6 dB increment, right? So this is how we would set up our magnitude plot, right? So this is fixed. Therefore, when you start, you just, this is given. What you need is only to mark this side, okay, with the relevance magnitude, okay? Always increase by 6 dB, okay? So it would say that here, every doubling of frequency will cause 20 log omega to increase by 6 dB, okay? Therefore, the line will increase equivalent to 6 dB per octave. Octave here referring to when the frequency is doubling. Okay, doubling here is not is when it become 2. Okay, become this is 1, then it become 2, double lah, right? So then the frequency become double, then it will increase to 6 and so on. Okay, so in terms of how should I say? In terms of per decade now, okay, 6 dB is per octave, okay, when the frequency is double. Therefore, when we convert it into per decade, okay, per decade means 10 times, okay. Octave is double the frequency, decade is 10 times the frequency, okay, from A to 10 times of A, right? Therefore, the increment would be 20 dB, all right? So what we would do from this is that we define the low frequency region, okay? The low frequency region, which is before A, okay? Because in our previous conditions, we say that this is the low frequency, okay, when it's approaching 0, then we get A, right? The frequency is A with the magnitude 20 log A. Therefore, here we just plot for A and lower frequency than that, it will have some magnitude almost similar to 20 log A, right? That would be the magnitude, right? So this would be the starting point, okay? So in the exam or whatever, you may put 0, okay, 20 log A and so on. So you start somewhere here, okay? Just draw a straight line. This is an approximations, right? And we would say this A itself, okay, frequency at A is the break frequency. Okay, we call that as a break frequency. The break between the low and the high frequency asymptote, right? Now, by using this slope, okay, this slope 20 dB per decade, okay, we know that now every 1 decade, or one decade over here, okay, every 1 decade, it will increase 20. Okay, so you will see that this point is roughly 20. Okay, 18, 19, 20, 20. Yeah, okay. This is approximately 20 lah, somewhere here. Okay, and if you draw this out, okay, also this represent doubling and it should give you 6 times. Okay, so 6 dB. Right? So basically, what you need is from this point to the next decade, okay, make sure you have increased 20 dB. That's all. Okay, so just draw that and plot that 2 point and draw a straight line. Okay, so this 100, it will give you roughly 40 lah, right? 20 should be 40. Okay, I guess yes, 40. Maybe my line is not correct lah, not proper lah. Okay, but it's somewhere like this. Okay, so maybe this line will be like this lah. Okay, slightly slanted a little bit. Okay, so this is how you can draw what we call as asymptote. Okay, asymptote is the straight line approximations. Okay, straight line approximations. Okay, so we just simplify our magnitude plot by drawing straight line for the row frequency flat. Okay, and for the high frequency one, okay, after the break frequency, which is A, therefore we will start to use the 20 dB, okay, slope. Okay, we draw a straight line over there. Okay, so this is how it would respond to the frequency. Okay, for its transfer functions. Okay, S plus A, right? Okay. And this is where we say begin at omega, okay, low frequency, okay, and it will also start for, it is representing the starting point for the high frequency approximations. Okay, 20, okay, draw the line. Again, this blue line, okay, this blue line is the actual one. Okay, actual line when you plot using software. Okay, in actual line, they will curve in this way. Okay, but for our own sketching, okay, we just use straight line approximation, straight line, okay, they meet, okay, and another straight line, that's all. Okay, so this is how we can plot for it, right? Then for the phasor plot, okay, phasor plot now, okay, what we would see, okay, is that we have to break them into several now. Okay, we start with the first thing, okay, the break frequency, which is at A. Okay, at A, it should be 45 degree. Okay, at A, it should be 45 degree. Okay, because of this this relationship lah, right? So it should be equals to aj 1, okay, plus a plus 1. So if you have 1 plus 1, which is same length, right, on in terms of x and y, so therefore the angle would be 45 degree. Okay, that is why we would mark as break frequency, we start at 45. Okay, then we know that, okay, at high frequency the phasor angle would be 90 degree, right? Okay, therefore we would use the 1 decade later. Okay, 1 decade later it should now increase up to 90 degree. Okay, we assume that 1 decade later, high frequency enough to have the phasor angle to be 90 degree. And because of that, okay, from 45 to 90, we can draw a straight line, okay, and with a slope so-called 45 degree per decades, okay. And when we go into the lower frequency as well, okay, it should drop back to 0, okay, because all are in form of real values, okay. Therefore it will drop to 0, okay. So we would always plot the phasor diagram in this way, okay. Start with 45, then increase 45, reduce 45 for the two uh, 2 decades, okay, adjacent to the break frequency, right? So this is a simplified way of drawing it, all right? After that, okay, we just connect to 0 and connect to 90 degree, right? So high enough, all 90 degree, low enough, we assume all 0, okay? But in actual, this is how it looks like, okay? So the blue line will represent the actual plot itself, okay? But what we plot in final exam or for our own purpose of estimations, okay, to check whether the software is plotting correctly or not, okay, we just use the asymptote approximation, just use a straight line, okay? So that would be more than sufficient, okay? So remember what you have learned just now is only for one transfer functions, okay, which is s plus a, right? So we also realize that when we plot the magnitudes, okay, we always put 6 plus 20 log a and so on, right? So we try to normalize this, okay, meaning to say put divide by a common value of it, okay, to normalize it, and eventually we put in this form lah, much more easier. Just put 0, 6, 12, 18, okay, every time increase by 6, okay. And this one you have to label it yourself, okay. Either you want to use every 4 equals to 6 or every 3 equals to 6, okay, whichever convenient to you, right? Then yeah, okay, so therefore we can simplify this, okay, by putting values only in terms of writing it 6 plus 20 log a, okay. So we will have this formula, okay, as our magnitude, okay. Next would be on the second type of transfer functions, okay, when we have the denominator, okay, 1 over s plus a, okay. So for these conditions, the plotting is only actually reverse, okay, because from 1 over the same same polynomial lah, or whatever it is, okay, when we put it in, therefore you realize that it become minus, okay, meaning to say reducing, okay. So for the low frequency, okay, the butt plot will again start from 0, okay, still the same. But when we come to the high frequency after the break frequency, therefore we get something similar, okay, something similar but with a negative sign, okay. Previously is positive sign, now we get a negative sign, therefore it represents a reducing format, okay. What is the rate? same 20 dB per decades. Okay, so we just draw 20 dB per decades. Okay, this is the way to draw it lah, right? So same thing for the phasor diagram. Okay, since previously this one is 90 degree, but now it becomes minus 90 degree. So we start from break frequency minus 45, okay, then become minus 90, okay, and it should at the lower frequency it should start from 0. Okay, next is when we have only S. Okay, when we only the transfer function is consists only with S, therefore the frequency will now become simplified like A multiplied by J omega over A. Okay, and because of this, okay, it always depend on the omega. So here we will say that the functions only have a high frequency asymptote. Okay, because depends on this terms is dependent to the frequency itself. Okay, so only have the high frequency asymptote. Okay, regardless of where it start lah, right? Therefore, we don't separate it. Okay, like previous, after the low frequency, we draw a flat zero line, right? Okay, now for S, okay, we just continue to draw, okay, all the way down, okay, regardless of it. Okay, then for the phasor diagram, okay, as we know, this one will consist of plus 90 degrees, okay, and we do not have any low frequency segment, therefore all the way 90 degree. Okay, so as you would expect for 1 over S, it is the reverse form of S, therefore the magnitude will be continue to decrease and no low frequency segment, so all the way up, going down all the way, right? And for the phasor diagram, only minus 90. Okay, so now how we going to use all this knowledge that we have learned? Okay, those four transfer functions now can be combined, okay, to start to plot, can be combined to help us to plot this board diagram. Okay, so we would look at this example. We have K S plus 3 over S plus 1, S plus 2. So here we can realize that this form is S plus A, right? Okay, this is 1 over S. Okay, this is 1 over S plus A. Okay, same thing, this is 1 over S plus A. So basically, it is somehow related to the 4 types of transfer functions previously. Okay, and we also know that in plot diagram, all the effect is just arithmetic. Okay, either plus or minus. Therefore, if we can plot this one, plot this one, plot this one, plot this one together, you just have to plus or minus all the values in between them, right? Therefore, in order for us to plot this out, okay, first use only the open loop functions, okay, because this is similar to the root locus technique. Okay, we use the open loop functions, okay, to solve or approximate for the closed loop functions. Okay, so what we would do is this open loop would be the KGH lah, right? So you assume we already get the open loop KGH value over here. Okay. What we would do now is we normalize it. Okay, since this is S plus 3 plus 2 plus 1. Okay, so what we have in our 4 typical format is S plus A. So this A, and this A must be same. Okay, so what we do is we try to normalize them. Okay, so how to normalize? So this is S plus 3, we can combine it as S over 3 plus 1, okay, multiplied by 3, right? So if we factor out the 3. Therefore, we have s over 3 plus 1. Same thing for this one, we factor 1 out, and this one we factor the 2 out. Okay, therefore, we have 3 over 2k, okay, as the factor. The rest now, the a is 1 plus 1 plus 1 plus 1. Okay, we have now normalized them. Okay, and the break frequency would be at a, right? And our a, previously we have 3, 2, 1. Okay, 3, 2, 1. Okay, so our break frequency would be at 1, 2, 3 lah. Okay, so quite straightforward. Right. So how we going to deal with that is 1, 2, and 3. So you will see 1, 2, and 3 is over here. Okay, so we will start to plot accordingly at this point 1, 2, and 3. All right. The magnitude should be gained from the lowest break frequency. Lowest break frequency would be the 1. Okay, over on from all these 3. Okay, and then we slowly increase lah. Okay, from there onwards. Okay. So what we can do from that particular plot, right? Okay, let's start from here lah. Okay, so what we do here, okay, as we know, s plus 3, okay, s plus 1 lah. Okay, we start with 1 over s plus 1. Okay, the lowest one. Okay, so we will draw straight line. Okay, then going downwards, right? Okay, so that represent the effect of this. Okay, this, right? Then for the second one, again straight line until 2. Okay, 1 means 1 over s plus 2, and then again go downwards, right? So go downwards. Okay, so that being represented by probably the, I guess it's the blue line. It's the blue line over there. Okay, then we also have this 1 over s. Okay, 1 over s. Okay, draw the 1 over s line all the way, and also s plus 3 line. Okay, s plus 3 line is this one. Okay, so go all the way, then move up. Right, so what we would do is we try to combine all this effect together. Right, later I think we will see how we can combine them together. Right, so from this we start at omega equals to 0.1. Okay, 1 decades before. Okay, and we would define the value of the functions. Okay, so we will say that s equals to 0 for the low frequency is given by such. Okay, therefore the actual s terms will be in the denominators, and we start to plot. Okay, the minus 20 dB per decade. Okay, this is the 20 dB per decade. Okay, then on the other hand, where is this 3 over 2k? Okay, 3 over 2k. Okay, where is this? Is we will combine this. Okay, assuming 1 decades before 0.1. Okay, so divide by 0.1, we would roughly get 15k. Okay, so the effect of this k is now moved to the magnitude by the value of this lah. Same thing, 20 log k, right? And from there, we would choose the k equals to 1. Okay, the magnitude can be denormalized, okay, later for our calculations. Okay, just plot accordingly. Then from there, the second part, the third part, and the final part, right? So to make our life easier, okay, we normally would form this table, okay, because on the line a bit difficult for me to like show it because very close, right? So what you will do, maybe in the exam you will start to draw this table first, okay? So what you once you draw this out, okay, therefore you will identify this is 0, this is 1, this is 2, and this is 3, right? So you will put 0, 1, 2, 3, right? So this is pull, pull, pull. This is 0, okay? Pull, 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 0, right? So you have three frequency to start, as I mentioned previously, okay? 0.1, okay, 1, 2, and 3, all right? So you would start to analyze according to your knowledge, right? So the knowledge would be for 1 over s, okay? This is 1 over s, right? Okay. We know that the magnitude would be always minus 20, okay, because of the slope is minus 20. So you just put minus 20 all the way from lowest to the highest, lah, all the way minus 20, okay, to denote uh, the slope of the magnitude, okay. Then at the pool at frequency 1, okay, this is 1 over s plus 1. From this, we would notice that the break frequency will start at 1, okay, meaning to say it will only start to minus 20 at 1, okay. So after 1, minus 20, minus 20, minus 20. Low frequency, 0, okay. For the pool at number 2, okay, the 1 over s plus 2, same thing, okay. It will start to have the gradient minus 20 at 2 and after 2, right? The rest, 0. Okay. Whereas for the 0 at 3, it will increase, right? But then it will start to increase only at the frequency 3, okay? Increase how many? 20. The rest, 0. Okay. So what you would get, okay, you just sum them up. Okay. You realize that here the slope is minus 20, minus 40, minus 60, then minus 40. Okay, so this is how it would contribute lah, towards the whole things, okay. And then once you get this one, you also calculate the starting point, okay. Since our plot over here is start from 0.1, okay, so if we going to plot for starting point at 0.1, what we would do is that we use k equals to 1, okay, and frequency 0.1, okay, frequency 0.1, and put it into our calculations, okay, you will get 20 log 15, okay, that 15 is this one, okay. Remember, we assume k equals to 1, okay, so you get this one, okay. Omega is 0.1, you get this, okay. Therefore, your starting magnitude would be 20 log 15, okay. Press from your calculator, okay, try to press your calculator later on so that you make sure you get this value, okay, 23.52, okay. Once you get this value, you will put this 23.52, okay, and start to apply this minus 20 dB, meaning to say 23.52 after 1 decade. After 1 decade, this one should be 3.52, okay, minus 20, right? Then at 1, now it will go further, okay, minus 40, okay. So after 1 decade, it should be minus 40. So you should expect this one minus 40. So you would get roughly minus 37.48, okay, somewhere here, right? But we will draw a straight line connecting over here, okay? Connect this line only, right? But what we need is only up to this segment, okay? Up to 2 only, okay? Because 2, it will have another uh, more steeper gradient, okay? So get this value, okay? Draw the line again, continue in this way, lah, okay? So from here, you will just continue to plot accordingly, right? So if you have a straight rulers, okay? If you have a straight rulers, okay? How you can plot it easier is that, let me erase some of it first. Okay, because you may have to write a lot of things, right? And it may not as easy as it is lah. Okay, sometimes the line run away. Okay, so if you have a straight rulers, okay, mm, okay, okay. So let's say you have a straight rulers. What you need to do is make sure your rulers is setting on this point to this point. Okay, just put your rulers in this way lah. Okay, then push your ruler up, okay, so that it coincidence with this, okay, so you can approximate, draw this line, that's all, okay. Then for this minus 40, you just use this point to minus 40, okay. Again, adjust your ruler in this way, sorry, not too straight, okay, but later you just use your ruler, okay. Try it, okay, put it in this way. At this point, now push your ruler up so that the ruler is parallel to this line. Okay, so draw until point A. Okay, then for this minus 60, again, your ruler all the way like this lah. Okay, then push it from this point, you draw the line. Okay, this is how you can plot it without calculating. Okay, but what you need is the starting value. Okay, draw your starting values. Okay, then plot this out, then you just use your ruler to push, right? Okay, so eventually you will get this one lah. Okay, after you push your ruler, okay, 20 gradient, 40 gradient, 60 gradient, then 40 gradient again, right? So eventually we'll see that you can estimate lah all this point, right? So if you don't look closer, then you will realize that this is a straight line only, okay? But there is a gradient, 20, 40, 60, then 40 again, right? Push your roller. And for plotting the phasor diagram, okay, the phase diagram now, okay, what you need is something similar, but because of the starting and the ending is 1 decade before and 1 decade after, right? So the work would be a little bit more tedious, okay? But nevertheless, it is the same, okay? You just have to identify the starting phasor, okay, and also draw this table, okay. Same thing, this is 1 over s plus 1, okay, and we know that we would plot 1 decade before and 1 decade after, means this will start at 0.1, okay, and 1 decade after, which is 10, right? So you put 0.1 and 10. All right, we don't use the break frequency lah. Okay, so same thing for this one, 1 decade before 0.2, 1 decades after 20. Okay, for 0, 1 decades before 0.3, 1 decades after 30, right? So the starting would be like we know that for this 1 over s plus a, okay, it will start from minus 45 all the way. This is representing the slope, okay, minus 45 all the way down, okay, until when it will start from 1 decades before until just on that decade lah, okay, one decade after. So you put 0 over here, okay. Same thing for this one, minus 45, minus 45, minus 45, 0. Okay, then for the 0 is going up, so 45, 45, 45, 0, right? Then also don't forget there is 1 over s. Okay, so this 1 over s represent minus 45 for all cases. Okay, minus 45, minus 45, minus 45. Okay, something like this. All right, is it? No, sorry. For 1 over s is a flat line. Sorry. Let's check again. I guess it's one. Yeah, straight line. Okay. So 1 over s is straight line starting from minus 90. Okay. So what we would do here, the starting line minus 90. Okay. Because of the 1 over s. Okay. So all the way at the lowest one, okay, starting at minus 90, then from there minus 45, okay, minus 45 all the way, okay, and then at 0.2 minus 90, this is 0.2, okay, then at 0.3 back to minus 45, same slope, okay, and nothing in between, so all the way same gradient, okay, until 10, okay, and then at 10 the line is 0, okay, 45 plus minus 45, so 0, a flat line, then increase back 45, okay, and then back to 0. Okay, so this is how you may estimate lah, okay, the phasor diagram. Right, so far any questions on this? Okay, so if no questions, probably we will end our sessions today here, okay, on just starting, okay, on how to draw the dot plot, okay, using the simple asymptote lines. All right, so after that, next week we will meet again to work further on the second order functions lah, right? So if no questions, then we will stop the recording here and see you again next Thursday. Okay? Okay. See you again. Bye-bye.
Thank you, doctor.
Thank you, doctor.
Okay.